So in this video, we're going to look at how to find the Laplace transforms using the table. All right, so it's probably going to be helpful if you print this table out and you have it next to you, so that way you can just kind of follow along with the rules that I'm going to utilize. So let's start off with a really basic example of how to use this, how to find a Laplace transform using a table. So we want to find the Laplace transform of this 4t to the third. All right, so to be able to do that, all we're going to do is we're going to start by defining it as a Laplace. So we're going to say Laplace of 4t cubed. And all you have to do at this point is you can just go ahead and factor the 4 out. And you don't have to do that, but just to kind of show how this works. And this is just going to be the rule where we can just go ahead and use our polynomial. So right here, we're going to use this t to the n. N in this case is going to be 3. All right, so we're going to have n is equal to 3. And we have the rule that we're going to have n factorial divided by s to the n plus 1. So that's going to be 4 times 3 factorial, and we're going to divide that by s to the n plus 1. So that's going to be s to the 3 plus 1. We can write this in a couple ways. We could write this as 4 times 3 times 2 times 1 over s to the 4th. We could write that as 4 factorial over s to the 4th, or we could just simply write it as 24 over s to the 4th. Any of these would be perfectly fine. Right? Much easier than using 3 integration by parts, which is what we would have to do to be able to find this without using the Laplace transform. A second example, we have this function g of t, and g of t is equal to 3t plus 2 quantity squared. So the Laplace of 3t plus 2 square, we're just going to FOIL this out. So that's going to be 9t squared plus 12t plus 4. And we're just going to go ahead and we're going to use each of the different polynomial, the polynomial theorem on each of these. And notice that we also have a constant. So we have f at t is 1 for 1 over s. And then we have, for just t, it's 1 over s squared. So we're actually going to use all 3 of these rules to be able to get to our Laplace transform. Right? So another way we can write this is we can write this as 9 Laplaces of t squared plus 12 Laplaces of t, and then plus 4 Laplaces of 1. Right? And this might be reminiscent of those limit properties or the derivative property if you did in Calc 1. Right? Now, we already know that this is going to be 9 times 2 factorial over s cubed. This is going to be 12 times 1 over s squared. And remember, if we just go right up here, we know that the Laplace transform of t is 1 over s squared. And then finally, the Laplace of 1 is 1 over s. So this is going to be 4 times 1 over s. And we can just go ahead and write this finally as 18 over s cubed plus 12 over s squared plus 4 over s. All right, that's our Laplace transform. Nice and easy. One final example of a nice and easy Laplace transform. We have this h at t, 4t squared minus 5 sine 3t. And so we can write this as, right away, 4 Laplace of t squared minus 5 Laplace of sine 3t. Right? Now we already know what t squared is going to be. In fact, t squared we just did in the previous example. So this is going to be 4 times 2 factorial over s cubed. And sine, we actually saw this one earlier. Remember, sine is k over s squared plus k squared. Right? And we actually proved this one. But we can just go right up here. And just in case we forgot, sine kt is k over s squared plus k squared. All right, so now in this case, k is equal to 3. And so what we're going to end up with is minus 5 times 3 over s squared plus 3 squared. Okay, or as a little bit more clean answer, this would be 8 over s cubed minus 15 over s squared plus 9. So hopefully that helps out when we're going through and trying to find these Laplace transforms. All right, they're not meant to be too difficult. The tables given to us, most students do very well with being able to find the Laplace transforms. All right. One final rule that we can implement is this translation theorem. And basically what this says is that if capital F is the Laplace transform of a function and a is any real number, then if we have a or e to the at of the function, then we just find the Laplace transform, and instead of s, we plug in s minus a. All right, so it's actually really easy to do this. So let's take a look at a couple examples of this. So we have the Laplace transform of e to the 5t, t to the 6th over 720. So we can write this as the Laplace of e to the 5t, t to the 6th over 720. In fact, we could pull the 1 over 720 if we wanted it out. All right. Now, we can use the translation theorem. Okay, and notice that right here, that a is equal to 5. All right, so this is a 5t. Right? So what's going to happen is that when we get the answer, whatever s is, we're going to replace with s minus 5. Okay, so right here, that's going to be s minus 5 when we get our answer. So we're going to translate as s approaches s minus 5. All right, and so that's all this does. Now, once we figure out what the translation is, we can go away and we can say this is really just the Laplace transform, and I'm going to factor out that 720 as well. So we can rewrite that as the Laplace. I just did the same thing. So that's 1 over 720 Laplace of t to the 6th. And I keep really wanting to write that 720 in there for some reason. So this is going to be t to the 6th. And right here, we're going to say as s approaches s minus 5. Right? So again, once we get our answer, the first translation theorem says we're going to replace with s minus 5. And so we're going to end up with 1 over 720. Notice that right here, n is 6. So we get times 6 factorial over s to the n plus 1, which is 7, as s approaches s minus 5. And for our answer, 6 factorial just happens to be 720. It's almost like somebody made this problem up. And so we're going to write this as 1 over s minus 5 to the 7th power. Right. So hopefully that makes sense as to how to implement that first translation theorem. Again, all you're going to do is you're just going to translate it by just kind of shifting it, in this case, 5 units to the left. All right. A second example of this, letter B, we have e to the minus 4t sine 2t. Now we know what sine 2t is going to be. That's going to be k over s squared plus k squared, where in this case k is going to be equal to 2. And this is going to tell us that s is going to approach s minus a minus 4. Right? So when we go to do our problem, we can set this up as the Laplace of sine of 2t as s approaches s minus a minus 4. Right? Or we could just say that this is going to be 2 over s squared plus 2 squared as s approaches s plus 4. And then all we're going to do is just plug in that s plus 4 when we go back in, and our answer, 2 over s plus 4 squared, plus 4. All right. Also notice that I believe that this is one of the more fundamental the more fundamental types of Laplace transforms that we have defined. So if we go all the way back up to our table, we do have e to the at sine kt. So we could have just used this if we wanted to. But it might be easier for us just to memorize this sine kt and just memorize the translation theorem since it's more universal. Right? One last example. So now we have t e to the t plus e to the 2t squared. All right? So a little bit tougher, but as you can imagine, what we're going to do is we're just going to go ahead and FOIL out. All right? So another way to write f at t is going to be t quantity e to the 2t plus 2e to the 3t plus e to the 4t. Right? Or if we want to go ahead and distribute the t through, that's going to be t e to the 2t, 2t, excuse me, e to the 3t, plus t e to the 4t. And now we can find the Laplace transform of each of those individually, and then take a first translation theorem on each one. So we're going to say that we're going to have Laplace of t e to the 2t plus 2 Laplace of t e to the 3t, and then finally plus Laplace t e to the 4t. Now another way to write this is that Laplace of t as s approaches s minus 2, right? Since in this one we have that a is equal to 2, plus 2 Laplace of t as s approaches s minus 3, since in this one a is equal to 3, and then, not surprisingly, in the last one, plus the Laplace transform of t as s approaches s minus 4. Right? And we know that the transform of t is just 1 over s squared. So this is going to be 1 over s squared as s approaches s minus 2, plus 2 over s squared as s approaches s minus 3, and then finally plus 1 over s squared as s approaches s minus 4. And finally, just back substituting each of those, we get to the final answer for this. So that's going to be 1 over s minus 2 squared quantity plus 2 over s minus 3 square quantity, and then finally plus 1 over s minus 4 quantity square. All right, so hopefully this illustrates how to go through and find Laplace transforms using the table. Most students do very well with this. It's really just algebra and then applying the rules. All right. What's not going to be as much fun is going backwards and using the inverse Laplace stuff. Okay, so make sure before we move on that you're okay with this, and then go ahead and watch the last video or second to last video, whatever it might be, when we go ahead and create the inverse Laplace transforms.